Hello and welcome to the instructional video for Unit 2, Lesson 3, Chopping Logs. Our jump start helps us to remember how we graph logarithms, and we're looking at transformations. This 2 means to go up 2, and this plus 3, you'd think it would mean to go right 3, but it actually means to go left 3. Now, of course, our reference point is 1, 0, and everything is relative to that. So this point will go up 2 and left 3. 1, 2, 3. Right there. Now, the asymptote also has moved. It used to be on the y-axis, and now it's going to come down over here. Now, some quick points that we can get from this new point right here are that it's going to go up 1 and over 1, up 1 and over 2, up 1 and over 4, up 1 and over 8. And getting closer to the asymptote, it gets halfway each time. Okay, so something like this would be a good graph. On number 2, we're actually working backwards. So our reference point right here. Now, does it have the same pattern of up 1 over 1? Yes. Up 1 over 2? Yes. Up 1 over 4? Yes. So I know this is log base 2. Also, they told me it's base 2. So I just need to track the transformation. That point right here is at 2, -5. Normally, I would find it at 1, 0. So it must have gone right 1 unit. It also must have gone down 5. So the function would be -5 plus the log base 2 of x minus 1. Now, in today's lesson, we're going to use graphs to discover a couple of important properties of logs. And of course, there's a story here between two students. So let's read the story together. Abe and Mary are working on their math homework together when Abe has a brilliant idea. Abe says, I was just looking at this log function that we graphed and falling off a log. And I started to think that maybe I could distribute the log. So what he's talking about is maybe I can apply the log to both of those inside things. He says, I guess I'm saying I think these are equivalent expressions. So I could just write it this way. But Mary says, I don't know about that. Logs are tricky, and I don't think that you're really doing the same thing here as when you distribute a number. So what do we think? How can we verify if Abe's idea works? Well, what do you think? I don't know. But think about test points or numbers that we could run through the equation to see if it actually works. So in number 2, it says, if Abe's idea works, give some examples that illustrate why it works. If Abe's idea doesn't work, give a counterexample. So we've often said that it's easier to prove things aren't true than to prove they are true. So it's easier to destroy than it is to create. So let's see. What if we had the log of, let's say, an easy power of 2, like 8 plus 16. Now, 8 and 16 would be 24, log base 2 of 24. And we're saying, is that equal to? I wonder. if it's equal to the log base 2 of 8 plus the log base 2 of 16. Now, the first log would be 3. The second log would be 4. So together they would be 7. Is that what the log base 2 of 24 is? Is it 7? Is 2 to the 7th power equal to 128? Or is it equal to 7? Well, log base 2, or 2 to the 7th, is 128. It is not 7. So it doesn't work. Doesn't work. And we call that a counterexample. Next page. Abe says, I just know there's something going on with these logs. I just graphed f of x equals log base 2 of 4x. Here it is. It's weird because I think this log is just a translation. That means a movement up or down, left or right, of log base 2 of x. Is it possible the equation of this graph could be written in more than one way? So in other words, where has the reference point gone? Well, it looks to me like the reference point is now here. And maybe that was a jump up of 2. How would you answer Abe's question? Are there conditions that could allow the same graph to have different equations? Well, let's think about that for a second. We know that sometimes things are equivalent to each other if they work. So the real test is, do they work? And yes, we have seen things that, for example, in a line, you can have y equals mx plus b. That's one form. But then you can also have ax plus by equals c. That's standard form. And they can both be the same line. So I would say, is it possible? Yes. Equations can have different forms. Different forms. Now, Mary says, when you say a translation of y equals log base 2 of x, do you mean that it is just a vertical or horizontal shift? What could that equation be? Find the equation for f of x that shows it to be a horizontal or vertical shift. Okay, so as I said before, I think that the reference point has moved up 2. And let's see if the pattern holds, since this is log base 2. Up 1 over 1, up 1 over 2, up 1 over 4, up 1 over 8. Yeah, it seems to be working. So the function appears to be 2 plus log base 2 of x. Now Mary says, I wonder why the vertical shift turned out to be 2 when x was multiplied by 4. I wonder if it has something to do with the power that the base is raised to, since this is a log function. Let's try to see what happens with y equals log base 2 of 8x and y equals log base 2 of 16x. So it says to write an equivalent equation for each of these graphs that is a vertical shift of log base 2 of x. So they've given you the graph, and again, look for the reference point. Okay, it's right here. This represents going up 3 from where we normally would expect that reference point to be. So this is the same as 3 plus log base 2 of x. And when we do 16x, you're going to find that right here at 4 above. So y equals 4 plus log base 2 of x. So think about the pattern. 16 gave us 4. 16 gave us 4. And 8 gave us 3. And 4 gave us 2. Are you detecting a power of 2? Mary says, next page. Oh my gosh, I think I know what's happening here. Here's what we see from the graphs. And she picks up on that right away. 2, 3, 4 comes from 4, 8, 16. Here's the brilliant part. We know that log base 2 of 4 is 2. We know that log base 2 of 8 is 3. And log base 2 of 16 is 4. So you can make a substitution. And you can make those equivalent to each other. Equivalent, equivalent, equivalent. So it says, I think it looks like the distributive thing you were trying to do. But since you can't really distribute a function, it's really just a log multiplication rule. I guess my rule would be, and there it is. That's the whole point of what we've been doing here, is right here. How can we express Mary's rule in words? So it would be something like this. The log of a product is the sum, S-U-M, of the factors. So, hold on, missed something. The sum of the log of the factors. Factors meaning the things that went into the product, the things that got multiplied together. Is this statement true? If it is, give some examples that illustrate why it works. And if it's not true, provide a counterexample. Okay, so let's just do one example. The log base 2 of, let's say, 32 is the log base 2 of 8 times 4. Now remember, log base 2 of 32 is 5. Okay, so is this the log base 2 of 8 plus the log base 2 of 4? And the log base 2 of 8 is 3. This one's that one. And the log base 2 of 4 is 2. And what do you know? 3 plus 2 is 5. Everything works as it should. Mary says, so, I wonder if a similar thing happens if you have division inside the argument of a log function. I'm going to try some examples. If my theory works, then all these graphs will just be vertical shifts of y equals log base 2 of x. So here's Mary's examples and their graphs. Test Mary's theory by writing an equivalent equation for each of these graphs that is a vertical shift of y equals log base 2 of x. So again, reference point right here, and that looks like it's down 2. And the next one looks like it's here. It's down 3. So this is going to be, and here's why I like to write the log with the vertical shift at the end, because that's the way the property works. And this would be minus 2, and this would be log base 2 of x minus 3. Again, 4 and 2 are connected, 8 and 3 are connected. Number 9, use these examples to write a rule for division inside the argument of a logarithm that is like the rule that Mary wrote for multiplication inside of a logarithm. Okay, so that would be something like the log base 2 of a division is the log base 2 of the top minus the log base 2 of the bottom. Is the statement true? You betcha. Let's see. The log base 2 of 8, remember 8 can be written as actually, let's go to 4. Log base 2 of 4 could be 8 over 2, and that should be the log base 2 of 8 minus the log base 2 of 2. The log base 2 of 8 is 3. Log base 2 of 2 is 1, and that's 2, and that's what this original log is equal to. One more property. Abe says, you're definitely brilliant for thinking of that multiplication rule, but I'm a genius. Oh, nice, he's humble. I'm a genius because I've used your multiplication rule to come up with a power rule. Let's say you start with log base 2 of x to the third. Really, that's the same as having 3 x's multiplied together. Those are the same. So I could use your multiplication rule and write it as 1, 2, 3 logs, and that's 3 terms that are all the same, and that makes it 3 log base 2 of x. So my rule is the log base 2 of x to the third is 3 times the log base 2 of x. If your rule is true, then I have proven my power rule. And Mary says, I don't think it's really a power rule unless it works for any power. You only showed how it might work for 3. And Abe says, oh, good grief. Okay, I'm going to say it can be any number x raised to any power. My power rule is log base 2 of x to the k is k times the log of x. Are you satisfied? Kind of sarcastic, huh? Provide an argument about Abe's power rule. Is it true or not? Okay, so it is true. We know that's going to be true. Because what we're saying is that if you have the log base 2 of x, and we kind of have to do a ... here. How many of them are there? There are, let's say, k of them. Right? So that's the same as saying log base 2 of x to the k power, But what he's saying is, well, you can break each one of these up to the log base 2 of x ... Well, this is added together in this case. All right, so plus ... plus a log base 2 of k of x at the end, and that happens how many times? K times, and so you can just put the k in front of the log. And then, yeah, it's not a formal proof, but it's pretty good. Now, Abe says, before we win the Nobel Prize for mathematics, I suppose that we need to think about whether or not these rules work for any base. The 3 rules written for any base greater than 1, and here they are listed. This is a super important box right here. Super important. Make an argument for why these rules will work for any base greater than 1 if they work for base 2. And the reason is logarithms are defined the same way for any base, and that ought to do it. Logs are defined the same for any base. So it should work. Okay, let's do quick takeaways on this. And so what we have just learned was a couple of things we've learned, and it's all in the box right here. I don't see why they want you to rewrite this, but we've learned 3 things: product rule, quotient rule, and power rule. Product, quotient, and power. And here they are right here. right down here. Okay, well, that's it. We're going to stop right there. See you next